Different engines operating in different ambient conditions will need different grades of oil. The grade of an oil is mainly dictated by its viscosity. Viscosity is defined as the measure of the internal friction of a fluid. A liquid that flows freely has a low viscosity, and one that flows slowly has a high viscosity. The viscosity of an oil will change with changes in its temperature. A cold oil will have a higher viscosity, and a hot oil will have a reduced viscosity. There are various standards employed to determine the viscosity of oils. They provide a standard by which different oils can be compared. The two standards which are generally employed in aviation are the Society of Automobile Engineers, or SAE, and the Seibolt Universal. Both systems use numbers to denote the viscosity. The lower the number, the thinner the oil. There are in use oils that have two viscosity values, for instance, SAE 1550. Oils with two viscosity values are called multigrade oils. They have the characteristics of low viscosity at low temperatures and high viscosity at high temperatures. The type of oil normally used in aircraft piston engines is mineral-based. However, some engine manufacturers have trialled and approved the use of semi-synthetic oils. If an oil contains no additives, then it is called a straight oil. A straight oil can be recognized by the fact that it only has an identification number. For instance, the bottle marked Oil 80 contains a straight oil. Note that the oil has a viscosity rating of SAE 40. Generally speaking, a straight oil is only used when running in new engines. However, there are certain requirements of some engines that straight oils cannot answer. To satisfy these requirements, additives must be mixed with the oil. These additives can take the form of antioxidants, detergents, and oiliness agents. Oils with additives are called compound oils. A compound oil of the same viscosity as the straight oil shown previously, SAE 40, would be kept in a container marked W80. This particular oil is used where specific cleaning qualities are required. Oil pressure and temperature readings, when interpreted correctly, are indicative of the mechanical integrity of the engine. A scan of the aircraft instruments must always include these vital items. The information they give may enable the pilot to take action which will prevent a bad situation getting much worse. As part of the pre-flight check, the oil contents must be ascertained to be sufficient for the flight we are to undertake. The oil filler cap must be secure, and a thorough check made to ensure that there are no oil leaks. Radial and inverted engines can suffer from a condition known as hydraulicking. This happens if oil accumulates between the piston and the cylinder head in the cylinders at the bottom of the engine. Because it's incompressible, if oil is trapped between the piston and the cylinder head on the compression stroke, a hydraulic lock will be formed. If the starter motor is being used to start the engine, then something will have to give. The piston might break, the connecting rod might bend, the cylinder may be torn from the crankcase, or the crankshaft may break. None of these is a pleasant prospect. To prevent hydraulicking, the engine must be rotated by pulling through on the propeller, after confirming that the magnetos are off before the propeller is touched. After engine start, the oil pressure must be indicated within a specified time. If the engine is started from cold, then the oil pressure may initially seem excessively high. However, as long as the oil pressure drops to normal as the engine warms up, this can be considered acceptable. If the aircraft you are operating has a dry sump engine, then its oil contents must be checked immediately after the engine has stopped, realistically within a few minutes of shutdown. This ensures that the tank contents are recorded accurately before the oil migrates into the sump under the influence of gravity. If, on the other hand, the engine has a wet sump, then a period of 15 to 20 minutes must elapse before the contents are checked. There are four main indications associated with a failure of the lubrication system. They are oil pressure too high, oil pressure too low, fluctuating oil pressure falling to zero. Too high an oil pressure with normal oil temperature may be a function of the pressure relief valve being set incorrectly, but this is unlikely unless the component has been worked on just prior to the flight. If, on the other hand, the high oil pressure is accompanied by a low oil temperature, the high oil pressure may be caused by the relatively high viscosity of the oil at low temperatures, making it difficult for the oil to pass through the engine. The oil pressure relief valve may be unable to control the situation completely until the oil temperature rises. As was stated before, as long as the oil pressure drops to normal as the engine warms up, this situation can be considered acceptable. However, if the pressure remains at dangerously high values, the engine must be stopped to prevent damage. Too low an oil pressure with normal or even low oil temperature could once again mean that the oil pressure relief valve has been set incorrectly. But as before, this is unlikely unless the component has been worked on just prior to the flight. The problem here is more likely to be excessive clearance on the bearings due to wear, or, potentially even worse, leaks from the output side of the pressure pump. If the minimum oil pressure cannot be maintained, then the engine must be stopped to prevent damage. If the oil pressure is too low with associated high oil temperature, then this is probably due to the temperature causing the viscosity of the oil to drop below the point where the oil pressure relief valve can cope. If the engine is fitted with oil cooler shutters, then they can be opened in an attempt to lower the oil temperature. Alternatively, if oil cooler shutters are not an option open to you, then consider either reducing engine power, or lowering the nose to increase airspeed, or even making the mixture richer. Any or all of these actions can be used to cool the engine and thus cool the oil, bringing its viscosity back up to the point where the system can cope. Once again, though, if the minimum oil pressure cannot be maintained, then the engine must be stopped to prevent damage. Small fluctuations of the oil pressure gauge needle, either side of the desired pressure, may be indicative of a sticking pressure relief valve. This would cause the pressure to first build up beyond the optimum level, then, subsequently, when the pressure reached a point high enough to overcome the stiction of the valve, it would open, dropping the pressure momentarily below the correct level. Then the cycle would start again. Large fluctuations of the oil pressure gauge needle, on the other hand, will probably be caused by insufficient oil in the system. The engine may have been leaking oil, and eventually the level will drop to a point where the pressure pump cannot sustain its output. Then the pressure will drop momentarily until the pump can get some more oil, when the pressure will rise again, if only for a moment. Again, if the minimum oil pressure cannot be maintained, then the engine must be stopped to prevent damage. If the oil pressure falls suddenly to zero, then perhaps the reasons may be a bit academic. After all, if the minimum oil pressure cannot be maintained, then the engine must be stopped to prevent damage, and there's probably not a lot you can do about the problem. Nevertheless, the probable cause is either failure of the pressure pump or a total loss of oil.